please. Okay, so we're going to continue. Can you see my screen, Daniela? No?
Yes, doctor.
Okay, good. So what we have to do now is take this and in here, this, put it in here, and this, put it in here. And we have to combine. Now, let's suppose that case of the bar, okay? So we put this into here, and then this is a square. So what we have to be careful is with the integration. So we have 1/2, okay? And so we integrate in x, okay? P of x squared, and it says divided by e, there. Okay, now here we have the a squared. So we could have dependence on x of the internal force, axial force, and also on the area. And then we need to integrate in a sectional area, dy, dz. Okay, this will give us a of x, and we can cancel one of these with this one here. Okay, I mean, we don't have enough space, so we're going to leave it like this. Okay, so it's going to be dx px squared divided by ea. The other one will cancel with this one, which is in the numerator. Here, for the case of the beam, we do something similar. Okay, so we have 1/2, we integrate in x, okay? Let's see, from 0 to L. And then this is mz, well, this is divided by e. We have mz of x squared divided by I sub c squared. And now in the section, okay, in the area, we have this y, and this is squared. So this is y squared. Okay, so again, this integral, you can recognize that it is equal to I sub c. So one of these will cancel. And finally, in the case of the shear, we have 1/2, the integral along the length of the beam. We have in dx divided by g. And then we have the shear force squared along the length of the beam divided by I sub c squared. That we integrate in the section the rest. So we have q divided by, this is a square times the section. Okay, and if we replace, this is what we obtain. So if we had a bar or a truss, that means that we have forces in the x direction. We are going to have the first term, this one here. So this is this one. If we have pure bending, this is here. If we have to include shear, this is what we are going to obtain. Okay. This is the type of expression that you need to apply in order to apply this methodology. Now, if you want to evaluate this, that means that you have to know P, bending moment, or V, a shear force. That means that the cases that at the first time we can analyze are just cases which are statically determinate, right? Because in this case, statically determinate cases, you can solve for the internal forces, P, M, or V. Now, axial force, bending moment, or shear force. And then you can plug it into here and obtain U. And that's what we're going to do in a minute, okay? we have to be careful because these are very long expressions, especially this one here, for example, this is quite common, okay? Okay, it's mc squared divided by I sub c, ei sub c. Sometimes I get confused here. So I'm giving you a warning. See, I play fair. So please be careful with this, okay? Okay. Now, let's try to apply this to calculate the deflection, to calculate the strain energy, elastic strain energy, right? So that's one step. And the other step is that we need to calculate the work developed, okay? And that's, remember the very first figure that I presented this morning is that I have a body, I have applied, and because of the elasticity, it deforms. So this point moves, and as it moves, it develops energy, right? So in general, again, we apply this force slowly increasing. So that's like an quasi-static. Remember in thermodynamics, you use this term, okay? So in general, okay, we have something like this, and we apply the force, okay? What we do is we consider that this force, it's applied in little pieces. We apply a little F and deforms a little bit. Then you increase another F, and then you increase, you displace a little bit more. Then increase another F, and it displaces a little bit more. So you go like this. So you apply a little F, deform like this. Then you have two Fs, and you displace a little bit more. Okay, so when you have two F, you displace one F, one delta only. That's the way it was explained in the video. So at the end, the work, okay, it's going to be equal to 1/2 F times delta. Why? Because the application of the force is not all at once, but slowly increasing, okay, to avoid any dynamic effect, okay? So we spent the previous subchapter talking about U. Now, in the place where we have this force, which is applied, the work developed by this force is equal to 1/2 F delta, and delta finally is the that I want to calculate, okay? So after we make these two equal, as you can see here, we make these two equal, then we're going to be able to calculate delta, okay? This is an example. I'm not going to do it, okay? This example, it was explained in the video that I asked you to view. So do you have any doubt to take the review of this video, or it is explained in the class notes, okay? This is in the class notes in page 65, okay? So this is class notes, page 65. People, you're responsible for reviewing this. I am not going to explain in class, okay? So again, you do this, apply the force. Because of this, of the elasticity, okay, you deform this delta, okay. Because of this elongation, you can have U. So in this case, let me go back. The U is going to be equal to 1/2 P squared over EA, okay. So you're gonna have U is gonna to the integral of 1/2 P squared over EA dx. And this one here is going to be equal to 1/2 the force multiplied by delta. And in this, you will be able to calculate delta. Okay, so you have to review that. I'm not going to do it here. Okay. Now, I'm going to present another example, which is in the class notes. It's a classical example, right? And in some cases, for example, here in the lab, right? I'm sitting right here in the lab, in the old lab. Okay, we had a beam, we apply force, and we measure the deflection, not the strain, the deflection. And we had some difficulties trying to compare theory and experiment, right? And the reason is that in some cases, the stress, the shear stress can affect the deflection. I say that again. The shear stress affects the deflection. Okay, for example, let's suppose I have something like this, right? Okay, and let's suppose I have a negative shear force here. Okay, because of this shear, okay, a little element here deforms like this. And you see that because of this is shear, you have this deflection. So you apply a force, a vertical force, you have some bending, right? You have the bending moment, you integrate twice and get double, right? But because of the shear, you have this effect. And this effect causes an increment in the deflection. How much? That's what we want to calculate using this energy method, okay? And now at the end, I'm going to make a comment because in some cases, it's worth to do this calculation. In some other cases, it's simply so small that you can neglect it, okay? So let's do that. And for that, we can use energy method. Okay, so let's consider, this is in your class notes on page 65. So this is on page 65 of your class notes. If you want to follow me. Class notes, page 65. Okay, so we have a cantilever beam with a concentrated force on the right end. Okay. Of course, we assume that it's prismatic, so the section is constant over the whole length of the beam. Okay, Mr. Paredes, is this a statically determinate beam or indeterminate beam? Mr. Paredes, Luis Paredes?
Is determinate.
Okay, tell me how many?
Static determinate.
Okay.
In two reaction in two equation.
So you have two reactions, and those are the reaction and the moment, okay, here, because this is clamped, okay? And of course, you have two equations to measure the forces in Y and to measure the moment in Z, right? So that's fine. So that means that we can apply the differential equation for equilibrium. Would you please remind me what's the differential equation for equilibrium?
Differential to the moment index over dx equal p x. Yes.
Okay. Okay. And okay, let's go to boundary conditions. Mr. Llanos, I'm not going to solve it. I just want you to practice. Okay, that's all. This is chapter 1, and this is solid mechanics. You review that. But I just want you to help you. Okay, that's all.
Yes.
So, Mr. Llanos, boundary conditions for this case.
Good morning, doctor. The slope is in the x equal 0.
Please. This is the equation that we are trying to solve.
Okay.
what's the function that we're trying to find, Mr. Young?
Oh, the PDX. In this
No! What's the function that you try to determine?
What is the
If
function?
you solve this, what are you going to obtain? If you solve this equation, what do you obtain? What do you obtain? Mr. Hidrogo, if you solve this equation, what do you obtain? Mr. Hidrogo, please.
The
Inertia.
the
No,
moment.
the what? I'm sorry?
The moment.
Yes, yes. This is what you're trying to obtain. This is the dependent variable. So from here, you obtain m sub c as function of x. If this is a second order equation, okay, you try to find the bending moment. Then, as boundary conditions, you could have either values of the bending moment or values of the first derivative. Mr. Ortega, Andres Ortega, tell me the boundary conditions for this case.
Good morning, doctor. X equal to 0, the deflection.
Me saying in this case, since it is a determinate beam case, okay, the function is the bending moment. That's the function that we're trying to determine. So the boundary conditions has to be either values of the bending moment or values of the first derivative. Okay, so Ms. Santos, tell me, what are the boundary conditions for this case? Ms. Santos.
At x equal to L, the moment is 0.
Okay, and the other?
And the other, that the shear force is equal to F.
F or minus F? I don't know.
And F,
Or minus F.
just F.
Do you agree, Mr. Cedeño, Axel Cedeño, do you agree is equal to plus F?
Yes, doctor, I agree.
Okay, let's see. If we make a cut, we close here, okay? The shear force here, it's positive
it's
downward.
Minus F, sorry.
Yes, the
No problem.
derivative
Yeah,
of
so-
Pfx is minus Px.
Yeah, so that means that those are the two boundary conditions. Here, the bending moment is 0, and here, very close to the end, V of L is equal to minus F. And you remember that V of L is equal to, what's the relationship between V of L and M? Mr. Villalba, do remind me, what's the relationship between this and M? Mr. Villalba, please.
The derivative of m is
Equal to
E of L.
V of L, is that correct? Or do I need something else?
Minus V of L.
Minus. Please, makes a big difference, okay? Plus or minus makes a big difference. Okay, that's it. I'm not going to solve it, and this is the solution. You can check it. So you can see that this is constant. And it's so the all over the beam, the shear force is equal to minus F. So at the end, it's going to be that. And you can evaluate this at L. So you're going to have equal to 0. So those are the two boundary conditions. These are the solution. So we have the two internal forces, and we can proceed for the integration to calculate U. So in this case, we have no axial force. So that's 0. So we're going to take this, put it into here. And we're going to take this and put it into here. Okay, immediately, this is going to give you a quadratic function. Please, if you don't feel comfortable integrating you have to review your calculus class notes because we need it. Okay, we need it. Okay, so we have to be careful, and that's it. So let's go on. So that's the Ms. Santos, do you have a question?
Yes, doctor. When we replace the actual load and the pure bending for the sigma x,
Yeah.
why we don't put like the factorization is ax squared to b and a and then b squared, like p to the square and bending moment by p and then a bending moment to the square.
If I understand correctly, okay, in this case, we have none of this. So this is not in our case.
But if were the case, the last part, you said that the energy method take the strength, the normal stress to the square. So if we had a actual load and bending moment, why we don't put like a bolts
yeah,
to the
what
square?
you can imagine is that if you have an axial force and a vertical force, right? So let's suppose that you do in steps. Okay, so let's suppose I have a force, the same load. Let's suppose instead of this, I have something like this, right? So I have a component in the axial direction, right? So you can think that we can analyze this in two steps, right? So we can say, okay, we're gonna have, in the first step, we're gonna have this, and in the second step, we're gonna have that. So if you have this, you have bending moment. If you have that, you have axial force. So that's, then you simply add them too. Okay? It's just basically superposition of effects. Okay? Miss Santos?
Doctor, so we couldn't mix them like px per moment?
But what I'm saying is that you could apply one, solve that problem, and then add the other one.
Okay.
Yeah, that's what we do. No problem. Okay, so this is what we do. Please be careful because in this case, explicitly, we are considering U for bending. Okay, just U for bending. So in this case, this is the bending moment, okay, that we deduced previously. And we can proceed to integrate and obtain finally this value. Since this is very long expression, recommendation as usual, we have to be careful with the units, with the units. So we go F squared, that's ln cubed, Young modulus, inertia, there. So we have 2 and 2 and 2 of these, that's 4, and we cancel that. 1/4, we got FL. So we're fine. Please, this is something that we should always do. We have to check our units, okay? Please don't write on my screen because I can get confused. Questions so far? People? Now, okay, now let's go to the more interesting part. Okay, so the shear. So this is the expression that somebody reminded us, Mr. Chinchin, I think it was. So it's shear force, first moment, inertia, and thickness at the cut. So let's go on. Let's remind some topics from chapter 2. So this is the section, okay? This is the section. So this is the first moment of here. This is the area, and this is the distance to the centroid. So the product of these two will give us the first moment. So this is typical, right? So it's B over 2, half of the h, half of the height squared minus y squared. Remember, this y is measured from neutral axis. Okay, this is something that we have employed during this in the previous chapter 2. Okay, so let me go back. One more. So we have the integral over the section of Q over B dA. So that's an integration that we have to complete. So here, okay. So this is tau xy squared. So this is shear force. That's Q divided by 2 and B. Okay. So we have B here in the denominator that has been canceled, and that's the inertia. This is, again, the force is a constant, inertia is a constant, and we can integrate this. We have to be careful because the dA, okay, the dA is equal to B dy. So this is constant, we can take that out. And the dy, you have dependence here, so we have to integrate. Okay? Result is this. Again, this is just an integration of a polynomial, a fourth order. It's easy to develop, to complete. And again, these are units. The units are very important. So we got F squared L. We have area, which is length squared. Units of G, it's F divided by L squared. So we got this, we got that. We have force length, which are energy. So we have this expression, okay, F squared L cubed over 6EI. That's the energy because of the bending. And now we have 3/5 F squared L over AG. That's the strain energy from the shear. So what we have to do is we have to add them up. And that's what we are going to do here. That's that. And now, on the right-hand side, on the left-hand side, you see that I have included the external work. Okay, that means that because of this, okay, and this is delta. Okay, again, this is 1/2 because the application of the force goes slowly increasing, and eventually we could obtain the full value. And here you can see the shape. Okay, on the right hand side, okay, the force is squared. On the left hand side, the force is up to the first power. So we can cancel, and we can see that we can obtain the deflection. Okay. In this case, this is the expression. And what we have done here is that in this case, here I have A, and you see that A is equal to B times H, and then the inertia is equal to B H cubed over 12, okay? So this A here was replaced like this, and we took some common terms, and that's the final expression, okay? This term here has units of force, length cubed over force over length squared, that's for E, and the inertia has units of length to the fourth. So I have 2 here and 2 here, that cancels that, F, and you get correct units. Okay. Questions about this process, people? Any questions? Okay, and finally here, a comment, very important comment here is that you see that the sign is positive, okay? Sign is positive. This means that the deflection points in the direction of the application of F. Okay, so in this case, F obviously is pointing downward. So since delta is positive, that means that delta points in the direction of the application of the force. Okay. Now, this is something which is very important. Okay. This is 3/2. Okay, so that's 0.6. Okay. This is 1.3 more or less. So we can say that this product it's about 1 more or less, right? So we have 1 plus h over L squared. Okay, so you can see that usually h, okay, that's the height of the beam, and this is the length. Okay, let's suppose that h over L would be 1 over 10. Okay, so if h over L were 1/10, right? That means that this term here is approximately equal to 1 over 100, right? That means that if we have the height equal to 1/10 of the length, if we were not include this term, the error would be 1%, which is not very large, okay? And that's usually the limit that we consider in general, okay? So if we have an h over L lower than 1/10, that means that if we neglect this term, the error will be smaller than 1%. And so in the typical calculations, we say that if h over L in general, if h over L is less than 1 over 10, in general, we consider that the shear effects are small. That's what we usually say, okay? I'm going to write it here. So this led to a general rule that when h over L is less than 1/10, shear effects are small and neglectable. Okay, as we said here, right? If this is less than 1/10, this is less than 1 over 100. So this is going to be 1.01. So that's very small. So we neglect this. We simply including an error which is below 1%, which is neglectable, really. Okay. Now, what happens in the case of the ship? Okay. In the case of a ship, for example, we could have L over B of 4 to 1. and B over D is about 2. Okay, so in general, I would say that L over D would be about 1/8 or so, maybe 1/9 in some cases. That's above 1/10. That means that in general, okay, we should think about the influence of the shear in the case of the hull. Okay, so that's the final comment on this thing. Okay, people, is there any questions about this? Any questions, any issues? Any problem, please? No?
Doctor, for the next quiz, do we have to deduce it?
In some cases, yes. Or not about the quiz yet. So I cannot say, but in general, this is analysis. When you do analysis, you have to do both things. You have to be able to deduce, so you know where these things come from. Or if I want you to tell me that, to prove me that you are able to apply, in that case, I will give it to you and you have to apply and calculate something. Yeah, but you are responsible for both aspects, deduce and apply, because this is analysis. Santos?
Okay, doctor.
Anybody else? Any other questions? Okay, before we leave, do you know that there is a homework running? Is there any problem? Any questions about the homework, people? Any questions about the homework? No? Mr. Hidrobo, do you have a question?
Yes, I mean, we have to do the second part of the assignment. We have to construct a 3D model in AutoCAD and
Yes.
analyze something.
Yeah. But you have a lot of experience coming from. Can you see the screen?
Yes.
Okay. Yeah. For the first part of the question, right? It says that it's the same example that we had in class, that we analyzed in class. Okay, so it's a length 40 meters. It's a rectangular section, right? Thickness is uniform, 8 millimeters, and simply supported on both ends. Okay, so I want you to tell me the shear stress distribution. Okay, and then for the second part, okay, you have the basic relations in the class notes, so you can apply the basic relations in order to evaluate the normal stress distribution in this section, applying Taylor's method. So on the deck, even though the deck is at a constant distance from the neutral axis, the normal stress is not uniform. The normal stress is not uniform. Okay, because of the influence of the shear. Okay, so yeah, you have to review the relations that are presented in the class notes, and then you have to apply it. Please review the deduction, right? Because you are responsible for both. And then in the third part, I want you to plot the axial distortion, okay? That's because I want to insist, right? You have a section. You apply a vertical force. So this section moves vertically and then rotates, but it stays, according to pure bending, stays straight, right? But now in chapter 2, we said, okay, we have to include the effect of the shear stress. And the shear stress does something like that. So this section rotated, but also it has a little bit distortion. So it's not straight anymore because of the shear. So I want you to have that figure, that picture in your mind. Questions about this this problem? I made a solution for this using finite elements, and you can see on the deck the variation of the normal stress. Mr. Carranza, do you have any question?
Yes, doctor. In the second part of the assignment 3, is considered the spacing of the girder obtain the distance of the bullhead?
In the plan that I asked, I sent you, I'll try. Okay. Fortunately, okay. In the plan, okay, you have something like this, right? It has transverse both heads. It has double bottom, right? And here you can see that there are some elements on the top. Okay, so it's a girder. Okay, so you have, this is the beam. Okay, this is X. So this is the beam. So then you have a girder. But also you have longitudinal bulkheads. But these are longitudinal bulkheads. So this is the spacing that you need to consider. So this is your beam. Okay, this is clamped here and clamped here. And then you apply force on the deck. And then you have longitudinals, and this is the number of these longitudinals. Remember, that's the number of the variable R, the parameter R in the DNV regulations. Okay, remember, in the table, you have one row for each number of R. So you have to see the plan and see how many longitudinal stiffeners you have on each of this span for the longitude, for the transverse girder. Mr. Carranza?
Yes, doctor. I confused the spacing of the girder on the longitudinal plan.
Yeah. So this is, okay, this is the girder. Okay, this is the girder that you have to analyze. But you have to be careful, because if you have a longitudinal bulkhead until here, you can assume that the girder is clamped here and here. So this is the span, the length of the beam. Now, for the loading, you have to consider the spacing, and that's the spacing here. So you consider the spacing and the pressure in order to calculate the force per unit length on the girder. And for the length, you go from here to here. That's L, to analyze the bending of the girder. Mr.
Thank you,
Carranza?
doctor.
Okay. Yes, about this assignment, okay, I think it's a very good idea if you start getting used to, getting familiar with the type of plans that you have to work when you get become an engineer, okay? So that's typical. You have a structural plan and you have to get information. So you get familiar, okay? Sometimes it's confusing, but yeah, review it, and finally you start making some sense, right? So if you take that information and make a 3D plan, okay, you start seeing this structure as projections, right, in the 3D plan. So that's for your own Okay, so that's the reason why I gave you this. Okay. But please, we don't have too much time, so you have to start working right away. Any questions, people? Any other questions? Okay, then that's all for today. You can stop the recording, Miss